Hello learners, welcome to this tutorial on Programmable Peripheral Interface 8255. How to interface an I/O device with 8085 or 8086 microprocessor. It can be done with the help of this Programmable Peripheral Interface. So for this tutorial, I will be referring this textbook, Uday Kumar, B.S. Umashankar, the 8085 Microprocessor, Architecture, Programming and Interfacing, Bsr Education, 2008. So, a 8255A is a general purpose programmable I/O device. It is designed to interface the CPU with its outside world. As we know that 8085 an 8-bit microprocessor, 8086 is a 16-bit microprocessor. In order for it to interface with input or output device, we need to have a supporting IC. So the supporting IC will enable the microprocessor to do transactions with the external world. So some of the I/O devices like ADC, DAC, keyboard, keypad, joystick, etc. If I want to interface such input or output devices with the CPU, we need to make use of this 8255 IC, which is a programmable peripheral interface. And the important thing with 8255 is we can configure the 8255 using a program without needing to rewire it or change any hardware component in it. We can just by changing a program, we can able to reconfigure our programmable peripheral chip. So here I show an interface diagram of 8085 microprocessor with 8255. So here we have 8085 microprocessor, which is an 8-bit microprocessor. So it has AD0 to AD7, where the address and data lines are multiplexed with each other. So this can be separated out with the help of a latch. We can make use of an 8-bit latch and using an ALE signal. ALE is an address latch enabled signal. We can separate out the address information and the data information. Then we have control lines like RD bar and WR bar, reset signal and IOM bar. IOM bar stands for whether we are going to do IO operation or memory operation. So this IOM bar can be used as one of the gate signal to your 3 to 8 decoder 74LS138, which is used for generating the chip select signal. So for generating the chip select signal, we can make use of A4, A5, A6 and A7 signal, and based upon the logic, we can generate the chip select signals using this 74LS138 IC. So this chip select signal will enable our 8255 programmable peripheral interface. So here you can see the D0 to D7 of your 8255 is connected to the D0 to D7 of your 8085, and pin number A0 and A1 is connected to the A0 and A1 of your 8085. So other pins A2 to A7 are used in your latch. So we use the RD bar signal, write signal. So if I want to, for example, if I connect some peripheral device to this 8255 in either port A, port B or port C. So all ports, port A, port B and port C are 8-bit ports. So port A, PA0 to PA7, port B0 to B7, port C0 to C7. All are 8-bit ports. Thereby I have 24 input or output lines. So I can connect some input or output devices. If I connect an input device, then I need to read the input device. For that we make use of this RD bar signal. If I connect the output device, then the output has to be, or the data has to be sent to that output device. So then it is a write operation. So we make use of WR bar signal. Then we can also reset this 8255 to make it in a default mode. So that is how this 8255 IC is connected to your 8085 microprocessor. So here the important thing to note here is we have 24 IO lines. It is divided into 3 ports, port A, port B and port C. So each port is going to be of 8 bits. And this 8255 is a 40-pin chip and it is available in dual inline package. So the prominent features of 8255 are, it consists of 3 8-bit I/O ports, as I said, port A, port B and port C. The address and data bus must be externally demultiplexed. So that is what we do with the help of a buffer. It is TTL compatible and it has improved DC driving capability. D0 to D7 data bus lines are available to read or write data into ports or control register. So we already know we have 3 ports, port A, port B and port C. We also have a control register which is used for configuration of your 8255. So the configuration can be done with the help of this control register. So the ports as well as the control register can be read or written. Especially this control register, it can be written but it cannot be read by the microprocessor. Ports can be read as well as written by the microprocessor. So address lines A1 and A0, it allows to select which port or control register is used. For example, if I use 0, 0, A1 is 0, A0 is 0, then port A is selected. 0, 1, port B is selected. 1, 0, port C is selected. 1, 1, control register is selected. So depending upon the value available in A0 and A1, we can select the corresponding port or a control register. So CS bar is used to enable the 8255 chip. On reset, if a reset signal is applied to 8255, then all the ports, port A, port B, port C, are initialized as an input ports. So here 8255, it consists of 3 8-bit bidirectional I/O ports. So 24 I/O lines, port A, port B, port C, and it can be configured as per our requirement. I can either configure it as an input or as an output, but not simultaneously. Port A as an option of bidirectional port, where I can use it as an input as well as an output port. So port A contains one 8-bit output latch or buffer and one 8-bit input buffer. Port B also similarly, it contains one 8-bit output latch or buffer and one 8-bit input buffer. Port C, it can be divided into 2 parts. Port C lower, which is nothing but PC0 to PC3, and port C upper, which is PC7 to PC4. They can be independently programmed as an input or output line. So we can use port A as an 8-bit port, port B as an 8-bit port, whereas port C, I'm going to divide it into 2 parts. One is port C lower, which is nothing but PC0 to PC3, and port C upper, which is PC7 to PC4. And these port pins have the capability of sourcing 1 milliampere of current at 1.5 volt when it is programmed as an output pin. So these 3 ports, port A, port B and port C, can be further divided into 2 groups. We can make it as a 2 groups, group A, group B. So group A consists of port A and upper part of port C. Group B consists of port B and lower part of port C. So here I show a block diagram representation where we can group port A and port C upper. Port A and port C upper, this can be combined as group A. Port C lower and port B can be combined to form group B. And we can also control it in terms of groups. Group A control and group B control is also possible. So these 2 groups can be programmed. Group A and group B can be programmed in 3 different modes, either in mode 0, mode 1 or in mode 2. So we will discuss about these modes. mode, I have two basic modes. One is called as Bsr mode, another one is called as IO mode. So if we put a value into the control register, if its 7th bit in the control register is 0, then it will be configured in Bsr mode. Bsr mode is bit set or reset mode. If the D7 bit is 1, it will be configured in the IO mode. Bit set or reset mode is applicable only to port C. Port C pins can be either made to set or it can be given with a logic 0, reset. So port C can have a logic 1 or it can have a logic 0 on the pins. So either a pin can be set or it can be reset in the Bsr mode. So D7, if it is 1, then the ports are going to be in a IO mode. In IO mode, I have three subdivisions. One is called as mode 0, mode 1 and mode 2. So mode 0 is a simple IO port, which means it does not have any handshake signals. Whether the data has been received by the receiver or not, we will not worry about it. So we don't require a handshake signals. So in mode 0, all the ports, port A, port B and port C are in simple IO ports. In mode 1, we have the handshake signals. So handshake signals in the sense the return information from the device. So if I am going to send the data to some output device, then the output device gives me a reply that it has received the data properly. Same way, if it is an input data, if it has a data, then it will give a signal to the CPU so that the CPU can read the data. So some type of handshaking or message interaction will happen between the IO device and the CPU. So such type of mode is called as a mode 1. In mode 1, it is called as a handshake IO. It is applicable for port A and or B. So here in this case, port A and port B, the handshake signals will be available in the port C. So port C lower and port C upper will be used as a handshake signal for port A or port B. And in the mode 2, port A can be configured in a bidirectional port. So both data can be transmitted as well as received. Whereas in mode 1, I can either use it in the input mode or in an output mode, but not simultaneously. But in bidirectional mode, at some time we might need to send the data, at some time we might need to receive the data. So both the things can be done with the help of a port A. Whereas in mode 2, port B will be in either mode 0, which is simple IO mode, or in mode 1, which is handshaking mode. So if it is in a handshaking mode for port B, the port C bits will be used as a handshake signals. So that is how the configuration of our 8255 takes place. So configuration takes place with the help of a control register. So by putting a value of 0 in D7, we can enter into Bsr mode. By putting a value of D7 as 1, we can go into IO mode. So in IO mode, again I have three options: mode 0, mode 1 and mode 2. So first let us talk about Bsr mode, which is bit set or reset mode. As I said, it is applicable only to port C. It is not applicable to port A or port B. In this case, the control register, as I said, in Bsr mode, the D7 bit should be 0. Right? The D7 bit should be 0 to be in Bsr mode. And the D0 bit represents whether I want to set a pin or reset a pin. Set means putting a logic 1 at the pin. Reset means putting a logic 0 at the pin. Now which pin? Because port C has 8 pins. Right? So which pin should be set or reset? That is given by this D1 to D3. So if I put 0, 0, 0, then bit 0 of port C is selected. If I put 0, 0, 1, bit 1 is selected. If I put 1, 1, 0, bit 6 is selected. So depending upon what is the value for D1 to D3, the corresponding bit of port C is selected. After selecting the port, I can make the port pin to go to high or low by setting this D0 bit. So this is what happens in your bit set or reset mode. Next, let us talk about IO mode, input or output mode. As I said, in input or output mode, the control register D7th bit should be 1. It should be set to 1. So now it is in a IO mode. In IO mode, I have 3 modes: mode 0, mode 1, mode 2. Mode 0 is simple IO mode, mode 1 is handshaking IO mode, and mode 2 is bidirectional IO mode. So here the bits D6 and D5 is used for selecting the mode for port A. So port A can operate in 3 modes: mode 0, mode 1 as well as mode 2. So I have going to use 2 bits D5 and D6 for selecting the mode for port A. So if we put 0, 0, then mode 0 is selected for port A. 0, 1, mode 1 is selected. 1, 0 or 1, 1, mode 2 is selected for port A. So we also need to set whether the port is configured as an input port or an output port. For that, D4 bit is used for IO function of port A. If it is set to 1, then the port A is configured as input port. If it is 0, then the port A is configured as output port. Same way, D3 is used to define the IO function of port C upper. Port C upper is PC4 to PC7. So here also we specify 1 means input, 0 means output for the port C upper pins. Then D2 is for mode selection of port B. So port B can operate only in 2 modes. It does not have a bidirectional mode. So it can operate either in M0 or M1. So 0 means M0, 1 means it will be in M1. Same way, D1 is used to represent the port B, whether it is acting as an input port or an output port. It's an IO function of port B. So 1 means input port, 0 means output port. Then D0 gives the functionality for your port C lower, whether it is an input port or an output port. So 1 means input, 0 means output. So that is how we can select the mode of operation. Port A can operate in 3 modes: mode 0, mode 1 and mode 2. Port B can operate only in 2 modes: mode 0 and mode 1. Port C is used in a bit set or reset mode, or in a simple IO mode, or it can act like a handshake signals for the port A and port B. So the functionality of the ports are also defined. So 1 for input port, 0 for output port. So mode 0, it's a simple IO or basic IO. So here port A and port B is used as a 2 8-bit ports, and port C has 2 4-bit ports, port C lower and port C upper. So either the ports can be in input mode or in output mode, but not simultaneously. The outputs are latched, but the inputs are not latched. Which means if the CPU wants to send some data, so it can send the data and it need not refresh the data again and again, because the data will be latched and it can be easily read by the output device. Whereas input devices need to retain the value in the pins until it is read by the CPU. Since the data is not latched, since the inputs are not latched, the input device must retain its value. It must retain its value for a certain time period. Until the CPU reads the data should be retained. So that is very important for your mode 0 operation. So in output configuration, outputs are latched, whereas in input configuration, inputs are not latched. It can be used for reading the status of the switch, but not for reading the keyboard, because keyboard, when I press it, the data should be latched. Then only it can be identified which key is pressed. Whereas in case of a switch, we can sense whether the switch is pressed or not by continuously checking the values. In mode 1, it is called as a strobed IO or handshake IO. So it is very useful when an input device supplies data to the microprocessor at irregular intervals. If we don't know when the data arrives, so it can arrive at any point of time. So in that case, the handshake signals will be really helpful, whether it has reached the destination properly or not. Once it has reached, then the device can send the next data for further transactions. So there the handshake signals will be really helpful. So in strobed IO or handshake IO, port A and port B is used as a 8-bit IO ports, and port C is used as a handshake signal for port A and port B. So for port A, port C upper will be used as a handshake signal, and for port B, port C lower will be used as a handshake signal. So in port C upper and lower, we have 4 lines. Right? Upper is PC4 to PC7. For lower is PC0 to PC3. Out of these 4 lines, 3 lines will be used as a handshake line for port A or port B. If I am going to use only one port in handshake mode, either port A or port B, in that case, 5 lines, because 3 lines will be going for the handshake signal of either port A or port B. So remaining 5 lines can be used as a normal IO pins. In mode 2, it is a bidirectional handshake IO. So in certain situations, at certain time we need to transmit the information, at certain time we need to receive the information. So that can be done with the help of a bidirectional handshake IO port. So here port A alone can work in the bidirectional nature. Port B can't. Port B can work either in a simple IO or in handshake IO. It can't work in a bidirectional IO. In the bidirectional handshake IO, port A uses 5 signals from port C as a handshake signal. It uses 5 signals, not 3. Okay, in a bidirectional mode, port A uses 5 signals. If port B is configured in an handshake signal, it will use the remaining 3 pins of port C as a handshake signal. On a summary, port A can work in mode 0, mode 1 or mode 2, whereas port B can work only in mode 0 or mode 1. Port C, it can work as a mode 0, simple IO pins, or it can be used as a handshake signals for your port A and port B. When the 8255 is reset, the port A, port B and port C are initialized to work as input ports in mode 0. So now let us see the pin description of your 8255. So 8255, as I said, it's a 40-pin dual inline package. So here you can see port A 0 to A3, and here you have port A4 to A7. So this is your port A. Then I have port B 0 to 2 here, 3 to 7 here. So this is port B. Then I have port C0 to C3, C4 to C7. This is port C. Port C upper, port C lower. Then we have D0 to D7, which is a data lines connected to your microprocessor. Okay, these are the data lines connected to your microprocessor. So this data can be sent either through port A, port B or port C. Same way, if I connect some input device to any ports, the data can be received through this D0 to D7 and can go to your microprocessor. Then we have control lines like RD bar. While reading the data, it will be helpful. WR bar for writing the data. CS bar is for chip select. For enabling this chip, we can make use of this CS bar. VSS is ground, and A0 and A1 is used for selecting port or a control register. So 00 means port A, 01 means it will be port B, 10 means port C, and 11 means control register will be selected. And also we have a reset line so that I can reset our 8255. There is also a power supply line which is VCC. The signal lines with its directions are provided here. So D0 to D7 is bidirectional. P0 to PA7 port line. PC4 to PC7, again it is upper part of port C. Here we have a lower part of port C and port B0 to B7. So here I can configure this port A, port B and port C either in input port or an output port. Then I have supply lines here, chip select line, reset signal, A0, A1 to select port or control register. Then we have read or write signals. So this is the architecture of your programmable peripheral interface. So the data from your microprocessor, it comes through this D0 to D7. It goes into the data bus buffer. So this data bus buffer is connected to the internal data bus here. This internal data bus is connected to port A, which is PA0 to PA7. Then port C upper, PC4 to PC7, port C lower, PC3 to PC0, and port B, PB0 to PB7. So this group port A and port C upper can be controlled by this group A control. Same way port C lower and port B can be controlled through this group B control logic. Then I have read-write control logic, which provides the signal for data transfer. It has the control lines A0, A1 for selecting a port or a control register, read or write information, reset information, and also it has the chip select information. So this is a very simple architecture of your programmable peripheral interface. So a data bus buffer, it is a tri-state 8-bit buffer. So it can be used for both transmitting as well as receiving the data to and from the CPU. Control and status information can also be transferred using this data bus buffer. There is a read-write control logic where we make use of it for controlling the internal or external transfer of data or control or status code. Write signal enables the write operation. Reset signal is an active high signal. It clears the control register and sets all ports in the input mode. Chip select signal, a low on this input selects the chip. This chip select should be activated. Then only a particular port can be selected through this A0 and A1. So chip select is 0. Then if A0 and A1 is 0, 0, port A is selected. 0, 1, port B is selected. 1, 0, port C is selected. 1, 1 means control register is selected. So if I have a chip select to be 1, which means the chip is not selected, chip is not activated. In that we need not worry about A0 and A1. Any value, the IC is not going to work. Then we have a read signal which enables the read operation. Then we have A0 and A1. As I said, it has to be looked with the help of a chip select signal and also the control signals RD bar and WR bar. So 0, 0 means it is port A. 0, 1 port B. 1, 0 port C. 1, 1 control register. Right? So if I take 0, 0, so 0, 0, here we do read operation. So reading the port A. Here same way 0, 0, write operation, which means we are going to write the data to port A. 0, 1, we are going to read the data via port B. 0, 1, write, we are going to write the data to port B. Same way 1, 0, read the data through port C. 1, 0, write the data into port C. 1, 1, Here control register can be just written. It cannot be read by the microprocessor. So we have only one option. So 1 then writing a data onto your control register, configuring your 8255 IC. Then this 8255 can be connected in a microcomputer system either in a memory mapped IO mode or in a IO mapped IO. So memory mapped IO in the sense the IO devices are assigned a memory location, or the IO devices are addressed with the help of a memory addresses. In IO mapped IO, we have a dedicated address for each and every IO device. In 8085 memory mapped IO, we make use of 16-bit address for accessing your IO device. In IO mapped IO, we make use of 8-bit address for accessing your IO device. In 8086, we make use of 20-bit address for accessing your IO device in memory mapped IO. In IO mapped IO, we make use of 16-bit address to access your IO device. So for example, let us take, we need to access 8255 connected as a IO mapped IO with addresses for port A, port B and port C, and control port are 20, 21H, 22H, 23H. Which means the chip select signal should be selected. We already know that A1 and A0 will be used for selecting port A or port B or port C or control register. So 00 means port A, 01 means port B, 10 means port C, 11 means control register. So these two values comes from the last two bits of this address. So other bits 00, 10, 00, right? So this bits, it can be used for selecting the chip. It can be used for selecting the chip. So which means 20 means 0, 1, 0, 0, 0, 0, 0, 0. So these two bits goes as A1, A0. Remaining this bits is used for selecting the chip. So in addition to this bits, we also make use of IOM bar. Since it is configured in IO mapped IO, we have to specify 1 for IO, which means the chip will be selected. In case of a memory mapped IO, for example, if I want the addresses to be FFFC, FFFD, FFFE, 4F for port A, port B, port C and control part, then as usual, if I take FFFC means 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0. So these two bits will be used for A0 and A1. Other remaining bits will be used for your chip select signal. Here, since the IO device are configured in memory mapped IO, IOM bar signal will be 0. Now let us look at the interrupt driven data transfer operation. So as we know that in strobed IO or handshake IO, the port A and port B data transfer requires handshake signals. So these handshake signals are available in port C. And one of the signal in port C is INT. INT is for interrupt, interrupting the microprocessor. If it is a port A, then the signal is called as INTA. If it is port B, then the signal is called as INTB. So this signal INTA or INTB can be used for interrupting your microprocessor. It can be used for interrupting the microprocessor to either send the data or to read the data, depending upon whether the port is in input mode or in an output mode. So we can also have the other port lines which can be used for setting or reset the IE flip-flop in a 8085 microprocessor. So there is a IE flip-flop which is used for enabling the interrupt or disabling the interrupt. So 1 to the IE flip-flop means it enables the interrupt, 0 to the flip-flop means it will disable the interrupts. So that can also be done with the help of a port C bit set or reset control function. So I can make use of this port C line to enable the IE flip-flop in 8085 or disable the IE flip-flop, so that I can stop this interrupt from reaching the CPU, or I can allow the interrupt to reach the CPU. So now let us take an example. Let us take an input device that supplies data at irregular intervals. Let us assume it is connected to port B of 8255. So here I have 8085, here I have 8255, and we have connected an input device to port B of 8255. So it is going to send the data to this port B. Let us configure our port B to be working in mode 1. Mode 1 in the sense strobed mode or handshake mode. So it requires some handshake signals. So the handshake signals are 3 signals: strobe B, IBF B, and INTB. Strobe for port B, input buffer full for port B, and interrupt for port B. So these are the 3 handshake signals configured in mode 1 for port B. So now let us see how to interface this. So the interrupt line, it gets connected to the RST 6.5 of your 8085. 8085 has 5 interrupts: trap, RST 7.5, 6.5, 5.5 and INTR. Now let us assume that the interrupt signal from 8085, it goes into the RST 6.5. Then we have some chip select circuit for enabling the 8255 chip. There is a RD bar signal coming from your 8085, and the port selection will happen via A0 and A1. So here we will be specifying 0, 1 so that the port B will be activated. And the data D0 to D7 is connected to the data bus of your 8085 microcontroller. Since it is an input device, the data from input device goes to your buffer, port B buffer, and from this the data goes into your 8085 microprocessor. So we have 3 handshake signals supplied by port C. First one is strobe B, is an input pin to 8255. It's an input pin, right? It's an input pin to your 8255, and it is a low pulse. Okay, so low pulse of some 300 to 500 nanosecond duration. It is a low going pulse with a minimum width of 500 nanosecond. Whenever the device has some data to send to the port, right? Whenever the device has some data to send it to the microprocessor, it gives this low going pulse. Strobe signal is activated. Whenever the input device has some data to be given to the microprocessor, it will send this low going pulse. Once the strobe signal goes from low to high, then the data in the buffer, it will be read by the CPU. It will be read by the CPU. So for port A, we call it as strobe A. For port B, it is called as strobe B. In terms of pin, it is PC4 for port A and PC2 for port B. Next signal is your IBF, input buffer full. So this happens when the data is available in the buffer and it is not yet read by the CPU, right? So when the data is given by the input device and it resides in the buffer, so it is full, it is not yet read by the CPU. In that case, input buffer full status will get activated. It is an indication to both the peripheral and the microprocessor that data is available in the buffer. Then the microprocessor can read the data. Once the microprocessor reads the data, then the IBF will get deactivated. So for port A, it is called as IBFA. Same way for port B, it is called as IBFB. In terms of pin, PC5 for port A and PC1 for port B. Then we have the third handshake line, which is INT line, which is an active high output pin, which is used for interrupt driven data transfer. Whenever the data is available in the buffer, then the 8255 sends an interrupt signal to the CPU. Once the signal reaches the CPU what it will do? It will run the ISR, interrupt service routine. So in the ISR, it will try to read the value from the data line and it will try to make use of that value. So that is the use of having your interrupt signal. For port A, the interrupt signal is INTA. For port B, it will be INTB. As in the pin number, PC3 for port A and PC0 for port B. Now let us look at the timing diagram of this input device operation. So once the input device is ready to send the data, it will send a low going pulse. Okay, once the input device is ready to send the data, it will give a low going pulse. So within some 300 nanosecond, the data will be latched into the buffer. So my IBF signal will go to high. It will be retained high. Now the input buffer is full. After the input buffer is full, the interrupt signal will be generated. Within 300 nanosecond, the interrupt signal will be generated so that it indicates to the microprocessor that the data is available in the buffer. You can read the data. So an interrupt signal is generated. Once the interrupt signal is generated, the CPU will assert the read signal. So thereby the data will be read from the buffer. Once the data is read, the signal goes to low. Again, IBF signal goes to low because the data has been read. So the signal goes to low. So this is what happens in your data transfer operation. So let me explain it once again. So first, if the input device is ready to send the data, it will give a strobe signal, low signal. Once the strobe signal comes, within some 300 nanosecond, the data from the input device will be latched into the buffer. So my IBF signal will go to high. Input buffer full will go to high. Once my input buffer is full, within some 300 nanosecond, the interrupt signal will be generated by the 8255. It indicates that the data is ready in the buffer and the microprocessor can read the data. Once the interrupt signal has reached the 8085, the 8085 will assert the read signal. Once the read signal is done, the data in the buffer will be read, and after reading, the IBF signal will go back to low. So that is how the input data is being read by the CPU. Now let us look at how to send the data to an output device. So an output device that needs data at irregular intervals. So let us connect the output device again to port B of 8255 and configure the port B in mode 1. So here we are going to connect an output device to the port B. And again we have three handshake signals. One is OBF, output buffer full, acknowledgement signal, and interrupt signal for port B. And as usual, we have A0 and A1 for selecting the port B. You have to put a proper bit pattern here and a chip select signal to enable the 8255 chip. D0 to D7 is connected to the data line of your 8085, and the INTB is connected to RST 5.5. So now let us look at how this operation is being performed. So whenever a device needs a data, whenever an output device wants a data, it will make a request through this acknowledgement signal. Once acknowledgement is received, an interrupt will be generated so that it reaches your CPU. So then the data from the CPU will go into your port B. Once the data is available in port B, then the output buffer full status will be indicated then the data will be latched to your output device. So that is how the output device is going to work. So let me repeat it once again. So whenever an output device wants a data, it sends this acknowledgement signal, which is a active low signal. Once this signal is received by the 8255, 8255 sends the interrupt signal to the 8085 microprocessor. Upon receiving this 80 interrupt through RST 5.5, the data from microprocessor will be sent to your port B. So once the data is available in port B, the output buffer full will be indicated, and that signal can be used for triggering the output device to read the data from the port B buffer register. So the acknowledgement, as I said, it's an active low acknowledgement input signal. So the peripheral sends a low going pulse with a minimum width of 300 nanoseconds. Whenever it wants to receive a data, whenever the peripheral device wants to receive a data, it will send this low going pulse. So for port A, it will be called as acknowledgement A. For port B, it will be called as acknowledgement B. In terms of pin number, it will be port C6 for port A and port C2 for port B. Then the second control line is OBF line, which is an active low output pin, which indicates output buffer is full. It also indicates that the data is available for the output device to be read. So usually this output buffer full goes to logic 0 within 650 nanosecond after WR goes to logic 1. So for port A, it is called as OBF A. For port B, it is called as OBF B. In terms of pin number, PC7 for port A and PC1 for port B. So now we have the third signal, which is an interrupt signal, which is an active high output signal, which interrupts the microprocessor for sending the information. For port A, it is called as INTA. For port B, it is called as INT. Handshake pin, PC3 for port A and PC0 for port B. Now let us look at the timing diagram for this output operation. So whenever an output device is ready to accept the data, it sends the acknowledgement signal, which is a low going pulse. Once the acknowledgement is received, right? So at that time, the output buffer, which is an active low signal, here right now it is high, which means the buffer is empty. Once the buffer is empty, the interrupt signal will be generated, right? Once the interrupt signal is generated, the write information will be accepted by the microprocessor, thereby the data goes into the buffer. Once the data goes into the buffer status goes to low, which indicates, this indicates the buffer is full. Then the data is read by your output device. So let me repeat it once again. The operation is very simple. When the output device is ready to accept the data, it gives a low going signal of 300 nanosecond minimum duration. At that time, the output buffer full is not activated. Okay, it's a remember, it's an active low signal. Here I have high, which means the buffer is empty, right? Buffer is empty. So after the acknowledgement signal is received, an interrupt signal will be generated by the 8255. On sending this interrupt signal to the CPU what it will do? It will write the information from the data to the buffer, port B buffer. Once the data goes to port B buffer, what happens? Now the data is residing in the buffer. So which means the output buffer full will get transitioned to 0 from 1. Which means this is the buffer full indication. Then the buffer will be read by your CPU. So that is how the data is returned into an output device. So in this tutorial, I have discussed about how to use a programmable peripheral interface, which is 8255 IC with your 8085 microprocessor. Similar principle is also applicable for your 8086 microprocessor. And how to configure it in memory mapped IO and IO mapped IO, and what is the timing diagram for both input operation as well as output operation. Thanks for watching.